Hi, I'm Shashvat, and my project was on creating an anonymous proof-of-stake cryptocurrency with zero-knowledge proofs and Algorand. So before I begin, I should probably explain what some of these terms are. So cryptocurrencies are a form of digital currency. And so as you can see, Alice is sending some money to Bob, and then later she's sending some money to Dan, and these are all transactions. And these transactions are grouped into things called blocks. Over time, new blocks are added to the blockchain. So one of the problems we have to deal with is we need to make sure that all users agree on the same set of blocks, or the same state of the blockchain. And so the most important thing about cryptocurrencies is that they have no central authorities. Instead, they have to use different consensus methods to make sure that all the users agree on the same state of the blockchain. The other thing is that they use encryption to guarantee that the currency can only be spent by the proper owner. And so the first cryptocurrency was Bitcoin. However, Bitcoin has many problems. So Bitcoin uses proof of work for decentralized consensus. However, as you can see in the diagram, just 4 mining pools or 4 entities in Bitcoin hold 51% of the hash power. And so essentially these 4 entities control the Bitcoin network. So Bitcoin is not decentralized. Also, it's estimated that it uses as much electricity as Switzerland. And Bitcoin's proof of work also each block takes 10 minutes to generate, so it's very, very slow. And so some possible solutions, one of the possible solutions to this is to use proof of stake instead of proof of work. So what is proof of stake? So in proof of stake, users reach consensus by voting. And this is usually done through committees. So as you can see here, we have a small committee of 3 people, and since there are 2 votes for block A is going to be the next block in the blockchain. Now, in proof of stake, a voter's impact is proportional to the amount of money that they have. And the assumption is that most of the money is held by honest users. And the reason for this is, say an adversary wanted to attack a proof of stake cryptocurrency. To attack it, they would first need to get a large percentage of that currency, and this would be very expensive. Second, once they start attacking the cryptocurrency, the price would drop, and so the attack would be even more expensive because they would be losing the money that they have. So Algorand is one kind of proof of stake cryptocurrency, and it has several features. So it's very fast. So each block takes about 1 minute to generate. Next, it has very low confirmation times. So essentially, as soon as a block is added to the blockchain, you know that it's going to stay on the blockchain. It won't disappear. And finally, it's generally more robust to user corruption than some other proof of stake schemes. So how does Algorand work? So Algorand consensus works in 3 main steps. So the first step is called sortition, and we're going to be focusing on modifying the first step. So in the first step, users randomly self-select themselves to be part of the committee. And the probability that a user is selected to be on the committee is proportional to the amount of money that they have. And this is why Algorand is proof of stake. Second, actually, as part of the first step, users have to generate a proof that they were self-selected properly. Otherwise, everyone could just self-select themselves and you would have a disaster. Once you have your committee, they execute a step in a smaller consensus protocol, and then the first 2 steps repeat until the smaller consensus protocol finishes. And then, once this finishes, all the users agree on the next block to add. Now, the thing with Algorand is that it's fully public, because to verify these proofs of committee membership, users need to have access to each other's account values. However, we want to be able to have an anonymous cryptocurrency like Zcash and Monero. And so what these things are able to do, they're able to hide the senders and receivers of transactions, and they're also able to hide the amount sent in a transaction. So the goal of the project was to create an anonymous proof of stake cryptocurrency. However, these goals seem to be opposing each other, because in Algorand, users need to have access to each other's account balances to be able to verify the sortition proofs. However, anonymity implies that users don't have access to each other's account balances. And so one of the ways we can get around this is by using the zero-knowledge proofs. So what are zero-knowledge proofs? Zero-knowledge proofs were first introduced as proofs that yield nothing but their validity. And so ZK snarks are one kind of zero-knowledge proof, and they can be used to prove the validity of any general statement, like NP statements. So how does this work? So let's say you have some publicly known C program, and you have some public input and some secret input. Only you know the secret input. So you can prove that when you run the C program on the public and secret input, you can prove that it will return true. So how does this work? For example, the public input might be the set of all coins in the cryptocurrency, and the secret input might be your coin. And the C program will return true only if the coin that you give it is in the set of all coins. So using ZK snarks, you can create a proof that you own some coin in the cryptocurrency. And most importantly, you won't reveal anything about the coin that you own. Now, the last thing we need to go over are coins and coin commitments. So in a cryptocurrency, you might be dealing with coin C, and the C might have a value V, a public key PK, and for our cases, it's going to have a serial number SN, which I'll talk about later. However, if your anonymous transactions are revealing these coins C, they're not anonymous. So instead of dealing with coins, we're going to be dealing with coin commitments. What is a coin commitment? You can think of it as a safe. So let's say Alice has a coin C, and she doesn't want to reveal the coin C. So instead, she takes the C and puts it in a safe. And she takes the safe and sends it to Bob. And so because of cryptography, Alice knows that Bob won't be able to figure out what coin C is inside the safe. At the same time, Bob, because of cryptography, knows that Alice won't be able to modify her coin C because he has a safe. So how are our transactions going to work? So we're going to use the same transaction structure as Zcash. And so an anonymous transaction is going to consist of a serial number SN, a new coin commitment CMU, as well as a ZK snark proof. And what does this proof prove? So it proves three main things. So the first thing it proves is that you own a valid coin. So in each anonymous transaction, you're going to be creating some new coins. And these are going to be stored in the set of all coin commitments. So first you need to prove that you know some secret coin CM old that's in the set of all coin commitments. And then you need to prove that you know coin C old such that its commitment is CM old. And so by proving this, you're proving that you own some coin that has been created before, and therefore it's valid. Next, you need to prove that the coin has not been spent yet. So in these anonymous transactions, you are not revealing the CM old that you are spending, because that would be losing some of your anonymity. So if you didn't prove that it hasn't been spent yet, someone could create an anonymous transaction that spends the same CM old multiple times. And we don't want this. And however, we can't reveal CM old because you're going to lose anonymity. So instead, you reveal the coin's serial number SN. And the serial number is essentially a unique identifier of the coin. So if someone tries to spend CM old twice, they're going to have to reveal the serial number twice, and then they would get caught. Finally, you need to prove that you aren't creating any money. And so to do this, you prove that the value of the coin C new is also the value of the coin C old. And then you prove that the commitment CM new is a commitment to coin C new. So if you prove all of these things, you prove that the transaction is valid. So how can we use this to have anonymous sortition? So the general idea is first you need to prove ownership of a valid coin. And this is the same as before. Now things start to differ. So before we reveal the serial number. However, we can't do this in our anonymous sortition proof. And the reason for this is suppose Bob is participating in consensus right now. And so he reveals his serial number. And let's say Bob participates in consensus tomorrow and a week from now. And let's say he participates every day. Each time he reveals his serial number, each time he participates in consensus, he's going to reveal his serial number. And so each time he does this, he's going to be losing some of his anonymity. So we can't reveal the serial number. So instead, we keep the serial number a secret, and we prove that it's not in the set of all spent serial numbers. So this, now we don't have to reveal a serial number, but what happens if Bob is trying to vote in the same round, but he's trying to vote twice using the same coin? Since we're not revealing the serial number, he could potentially vote twice. And so now instead of revealing the serial number, we're going to be revealing called the temporary serial number, which is similar to a serial number, except it changes from round to round. So if Bob is participating in consensus now and tomorrow, he's going to have different temporary serial numbers. But if he's trying to vote twice right now, he's going to reveal the temporary TSN, temporary serial number twice, and then he'll get caught. Now once you've done all three of these things, you can finally prove that the user was actually selected from the coin value B. So does this mean that we're done? Not quite. So one of the challenges we want to do is we want to retain Algorand speed. Algorand is very, very fast. Each block takes about 1 minute. However, the diagram here is of Zcash's transaction generation time. And so even with Zcash's new protocol upgrade, each transaction is going to take 7 seconds to generate. Now, our proof is actually much larger than a Zcash transaction because we have to prove more things. So our proof will take longer than 7 seconds to generate. And if you have a 60-minute block time and each user is taking 7 seconds to generate a proof, it's going to be too slow to fit within the 60 seconds. So we need to figure out a way to make this faster. And so we pursued many different methods. So right now we're using ZK snarks, but we looked at different types of zero-knowledge proofs, like bullet proofs and Grossahay proofs. And we looked at combining them in weird ways. But ultimately we found that the best way to improve performance was to replace the SHA-256 hash function with the MIMC hash function. And the reason for this is the vast majority of the things that you're proving in your ZK snark proof are just various computations of the SHA-256 hash. And so if you replace it, we can significantly improve performance. So in future work, we want to look at even faster computations. We also want to do a computational analysis of these systems because we're combining many different techniques and we need to make sure that they work even when we bring them together. And finally, we would like to implement this in code. So I would like to thank my mentor, Ms. Kyle Hogan, as well as the MIT PRIMES program, Professor Gerovich, and Professor Cindy Davidas.
So Sprout used SHA-256, right, for the Merkle tree of commitments.
Yes.
And Sapling uses what?
Sapling uses a different. It uses Pedersen hashes.
And you guys use MIMC and you're faster than Sapling.
Yeah, because what happens is, so Zcash changed the Merkle tree to Pedersen hash, but then their pseudo-random functions were still SHA-256.
Oh.
And so if you change if you use MIMC, you can also use that for the pseudo-random.
So we use MIMC for the pseudo-random, and MIMC is algebraic, or it's as an efficient circuit?
Yes, efficient circuit. It's designed for things like ZK snarks.
And is that the only thing that you guys changed in the snark, or other things as well?
That's the main thing we changed. We also have to change some slight things.
Any particular snark that you guys use? The Pinocchio snark? Or?
No, we were just looking at terminal. We were just looking at decreasing the circuit size.
Go ahead.
So roughly, those two hash functions at the end that you talked about, sort of, is the speed we're getting just this kind of, how do those two hash functions compare in speed? And do we get close to that actual amount of speed up by swapping between them?
So I have not implemented it, but so you're writing zero-knowledge proof as a set of constraints, and so SHA-256 takes about 27,000 constraints to express one computation. However, MIMC takes about 700, and so it's much, much faster.
Thanks.
Cool. Thanks, Shashvat, again. So we're going to take a 10-minute break. We come back at 4:35, but Slava's also wants to take pictures. So mentors and students come up here, and I guess parents can take pictures, but Slava's going to take some official